So the title of my talk is Polarized Quark-Gluon Plasma. The results which I will be presenting is based on this Alice collaboration work. And the outline of the talk is as follows. First, I will give a very brief introduction to high-energy heavy ion collisions, specifically pointing out that there are two important initial conditions: large angular momentum and large initial magnetic field. And this could contribute to a phenomena called spin alignment of vector mesons. These are spin 1 particles. And I will be discussing about the observable, how to look for this spin alignment, and results primarily from Alice experiment. And then some discussion with respect to what are the theory expectations and big results. Finally, I will summarize, but the results have some surprises and there are some outlooks. So this slide shows the time evolution of the relativistic heavy ion collisions. Two heavy nuclei like lead or gold, they come and collide at relativistic speeds. That's why they are depicted here as Lorentz contracted along the direction of motion. When they come and collide, a large amount of energy is deposited in a small volume. So the energy density is very large. That leads to high temperature conditions. If the temperatures are greater than of the order of 150 mega electron volt, then we will form a system of deconfined state of quarks and gluons. And this state of quark and gluons has been experimentally observed at RIC and LHC energies. This system of quark-gluon plasma, or QGP, expands, and as it expands, it does some work, and hence the temperature starts to fall. When the temperature falls below this transition temperature, which is of the order of 150 MeV, hadronization starts to take place. This system of hadrons continue to interact and expand, and when the inelastic collisions among these hadrons stop, it is called as the chemical freeze out, where the particle yields gets frozen. And when the elastic collisions also stop, it is called as the kinetic freeze out. The particles are no longer interacting, they free stream and come and hit our detectors. And this is one typical event display of particles coming and hitting a time projection chamber. As you can see, this is a very short-lived system, and also both in space and time, and that's why any measurements that we do are very challenging for such a system. So, two important initial conditions I would like to point out. When these two nuclei come and collide, there is the distance between, the perpendicular distance between the centers of the two nuclei is called as the impact parameter. For non-zero impact parameter collisions, if it's head-on, zero impact parameter, we call it as central collisions. If it is grazing collisions, like 2 times the radii of the ions, then it is peripheral collisions. And anything in between, we say non-central collisions. For non-central collisions, you can see that one nuclei is coming in this direction, the other going in this direction. It imparts a large tug to the system, and that would lead to development of large angular momentum imparted to the system. Also, the nucleons which are in this overlap region are called participating nucleons, and those which do not are called spectators. They are also made up of protons, and these are charged particles moving in relativistic speeds, and that gives rise to large magnetic fields, initial magnetic fields. Both these angular momentum and the magnetic field are perpendicular to the reaction plane. The reaction plane, as we all know, plane needs two directions. One is the beam direction and the impact parameter. The planes subtended by these two directions are called as the reaction plane, or also called as event plane. And the angular momentum and magnetic fields are perpendicular to this reaction plane. To give you an idea of how large these values can be, so here are some calculations. The initial magnetic field as calculated in this paper in a unit MeV square. Here is a translation of that to Tesla. It can be of the order of 10 to the power 14 to 10 to the power 15 Tesla, and it dies down rapidly with time as the particles move away, charged particles move away relativistically. So that's large magnetic field, and it dies down with time. Here is a calculation of angular momentum plotted in y-axis in units of h bar, and x-axis is that impact parameter, head-on collisions, peripheral collisions, and non-central collisions. And you can see that the angular momentum for collisions with impact parameter around 2 to 4 Fermi can be as large as 80,000 or 70,000 h bar. And these are very large angular momentum being imparted to the system, and this is a conserved quantity for our system. Now, just to give you an idea of the numbers, how large these are quite large, expected in heavy ion collisions. These are some values which we encounter in nuclear physics. If you try to look at it from vorticity point of view, these, as you will see towards the later part of the talk, it can be very large. And these are the typical magnetic fields that we encounter, and those are also very large. So this plays an important role in the various observations that we make and the evolution of the system. The question which we ask is, our system are made up of particles which have spin, be it in the quark-gluon plasma phase, or once it hadronizes, we have, of course, spin-half particles are there. I will show you polarization results for lambdas, which are baryons with spin-half. But most part of the talk, we will concentrate on vector mesons. These are spin-1 particles like K star and phi mesons. And we want to ask what happens to these in presence of large angular momentum. So can we experimentally see signatures of spin orbital angular momentum interactions for this relativistic QCD matter? So that is the question which we are asking. Remember, spin orbital angular momentum interactions is there in many areas of physics, starting from atomic physics, splitting of the energy levels, to nuclear physics, which is the magic nuclei, the cell model, and even in material science like spintronics, which is a new area, emerging area. So how does one try to experimentally see this spin orbital angular momentum interactions? We have considered vector mesons. These are like K star and phi. These are some of its properties. Similar order of mass, lifetime, of course, factor 10 different. They are spin 1. Dominantly, they decay to charged kaons and pions. This is K plus K minus. These have only strange and anti-strange quark contents, and this has light and strange quarks. In order to find out this spin alignment, we have to define what is called as the quantization axis. So first thing, there are two possibilities of the planes which we can define. One is the plane subtended by the beam axis and the momentum direction of the vector meson. Perpendicular to that plane is the quantization axis. The other possibility is a plane subtended by beam axis and impact parameter, and perpendicular to that is also can be a quantization axis. Then what one does is goes to the rest frame of the vector mesons. the decay daughters are back to back, the angle made by one of the decay daughters with respect to the quantization axis is the quantity of relevance. Why? Because this angular distribution tells us whether we have a spin orbital angular momentum interaction or spin alignment or not. How does that follow? The angular distribution can be expressed by using simple quantum mechanics and can be given by this expression where it depends on, apart from these angles, the helicities, the decay amplitudes, and the spin density matrix. The spin density matrix is a 3×3 matrix, and that is, we want to measure the elements of this spin density matrix. Now one can use the spherical harmonics to write that equation which I showed in this form, some constant times y ln theta phi. And these are elements of the spin density matrix. One can integrate over the azimuthal angle and have one as a simplified equation. Now this rho -1, rho 1, rho 0 are just the diagonal elements of this 3×3 spin density matrix. Suppose you have a spin 1 particle, it can be in spin states, the third components of -1, 0, 1, and all should be in a non-aligned system. It could be all of similar probability, 1/3, 1/3, 1/3. So the total probability is 1. So what these elements represents the probability that a vector meson is in spin state -1, 1, or 0. Okay. Now we have a normalized spin density matrix, so its stress should be 1. So one can reduce this to this form, where rho 0 is just the probability that the vector meson is in spin state 0. Now, if you plug in the value 1/3, that means all the states are equally probable, then this angular dependence goes away. This becomes 0. So if you plot the angular distribution, the angle made by the decay daughter with respect to the quantization axis in the rest frame of the vector meson, then if it is 1/3, not aligned, no spin orbit interaction, you expect a flat distribution. If there is spin orbital angular momentum interaction or there is some alignment, then the values will deviate from 1/3, and then the angular distribution will have a shape. Okay, for this specific case, this is how it should look. So that is what we are looking for in experiments. We are not the first in high energy experiments to look for it. E plus E minus collisions, people have studied this quantity rho 0, okay, and has measured it as a function of XF, both Opal collaboration, Delphi. And they have tried, their goal was to study the role of spin on production dynamics of vector mesons. And what we are trying to see is there any signature of spin orbital angular momentum interactions in heavy ion collisions? As you saw, the initial conditions allow a large angular momentum to be imparted to the system. Now let's come to the theory expectation. Here is one particular calculations theoretically. It expects that the alignments will be more for lower momentum, say below 1 GeV PT or around 1 GeV or below it should be large, and then it would, at high PT, it would approach the 1/3 value of rho 0. If you look at the impact parameter or collision centrality dependence, it would follow the trend as for angular momentum. Remember, angular momentum values are small for head-on collisions, peripheral collisions, and they peak in mid-central collisions. And that's what you expect for the alignments, should be larger for mid-impact parameter collisions. So those are the theory expectations. But subsequently there has been many other theory developments, and as in usual in heavy ion collision, it's a convolution of many phenomena, and that makes things little complicated, but measurements can only help in settling the issue. So one, if there is vorticity due to some reasons, then the rho 0 is expected to be below 1/3 because a negative contribution here of square of vorticity. Magnetic field can also change rho 0. It can make it greater than 1/3 for neutral vector mesons as per this work, or less than 1/3 for charged, electrically charged vector mesons, or charged K star, for example. Process of hadronization can also influence. It can make it less than 1/3 if hadronization proceeds via recombination of quarks. Or if it's fragmentation, it could be more than 1/3. These are given in this paper. And a new idea that if there is a coherent phi mesonic field, which also affects specifically the strange quark and anti-quark spin orbit angular momentum interaction, making rho 0 greater than 1/3. These could very well be competing with each other as well. So these are the theory and the physics process expectations. Now let's come to the measurements. All measurements that I'm showing here are through the ALICE detector, and this beautiful experiment and the detectors has already been discussed at this forum. I will not go into more details except to point out that the time projection chamber and the time of flight allows us to identify the particles to which the vector mesons decay, hence we can reconstruct them. The momentum information is obtained from the time projection and the inner tracking system, and to get an idea about the reaction plane, we use the measurements of V0 detector. How beautiful is the particle identification is shown here for the specific ionization energy loss of a charged particle in the gas medium of the TPC as a function of momentum. We could beautifully separate out the different stable particles that we detect in our detectors. It is so nice. This particular is, I think, for PP collisions. This has replaced the long-standing such a plot in the particle data book, and now the ALICE PID figures there. The resolution by which we obtain the reaction plane is important. That decides how well we know the quantization axis, and these are the resolution values of the various detectors which are used in ALICE, and they are pretty good. Now about the measurements, I'll be showing you results from PP collision at 13 TeV. They act as baseline. In many cases, the minimum bias PP collisions are baselines to heavy ion collisions. The results are for 2.76 TeV at mid rapidity. We will be looking at K star and phi vector mesons, but for null hypothesis test, we will also use spin zero K shot, which decays to pi plus pi minus. These are resonances. They are short-lived particles, so they have to be detected using invariant mass analysis. They sit on a large combinatorial background. Those has to be removed using some techniques called mixed event techniques. We have to correct for the finite acceptance and the response or the efficiencies of the detectors. The results are corrected for that. We will present result with respect to production plane, the plane subtended by beam axis and the momentum of the vector meson, as well as the event plane, which represents the plane subtended by impact parameter and the beam axis. We will randomize the event plane to again look at a null hypothesis test. Of course, they are all measured with finite resolution, and that has to be corrected for. With this, let me show you this, that we have reconstructed nicely the K star and phi vector mesons. These are, oh, I'm sorry for the font change. Okay, so these are K star signals, and this is a phi meson signal after removing the background, and you can see nice peak of phi and K star. How do we obtain the yield? We fit this K star to a Bright-Wigner function, and the area under that gives us the yield. You can calculate these in bins of momentum and the angle so that we get the angular distribution. Here in this particular case, the cos theta star is in this bin, and as a representative, the momentum is in this bin. The phi is a narrow resonance, so what we fit it to is a Voigtian function, which is a convolution of Breit-Wigner and a Gaussian function. The Gaussian function width represents the resolution with which we measure the momentum, and that affects the mass resolution. So that's why we use the Voigtian function to get the yields. Okay, so once we have the yields in bins of cos theta star, we can plot the yield as a function of cos theta star. Remember this cartoon, if there is no spin alignment, you would expect a flat distribution because rho 0, 0 will be 1/3, angular part vanishes. If there is spin alignment, you would expect some shape to this distribution. This is what one observes for K-star angular distribution in red-red collisions in a momentum bin below 1 GeV, and for mid-central collisions where we expect the effect to be more. This is with respect to the event plane. Okay. The blue one is with respect to the production plane. Again, you can see a shape is there to the distribution. These lines are fits using this functional form from which there is a normalization constant and the values of rho 0, 0 can be extracted. Now, to show you for a system where there is no such large initial angular momentum like proton-proton collisions, using same analysis technique and corrections, this is what you see, and it is pretty flat, the angular distribution. And if you look at K0 short, which is a spin zero particle, there also we do not see any angular dependence in the yields, both for production plane and the event plane. So now one can use this distributions to extract rho 0, 0, and its deviation from 1/3 will tell us something about spin orbital angular momentum interactions. Just to look in totality, these are the yields as a function of cos theta star. Remember, this is the angle made by the decay daughter with respect to the quantization axis in the rest frame of the vector mesons, and you can see there is some shape for event plane, both for K star and phi at lower PTs, and also in production plane. If we go to random event plane, then it is pretty flat, and if you look at spin zero particle, it's also flat. So they act as our baseline or null hypothesis tests with in addition